Welcome back. This will be our last video on the Laplace equation with a rectangle. In this case, we're going to look at some mixed boundary conditions. As you can see here, we have 1, 2, 3 Dirichlet boundary conditions and 1 Neumann. So it's a mixed, which is also known as Robin problem. So let's get right into it. Remember step 1, separate variables. We know what the answer is to this already. Right? We know that. We can now go to the boundary value problem. So we're going to be using, let's see here, we have x of 0 equals 0, x of a equals 0, and y of b equals g of x. No. Y prime of, yes, y prime of 0 equals 0. So we're going to use the x equation for the boundary value problem. Let's start with greater than 0. This would be positive mu squared. If this is positive, this is positive. So we're going to be left with the case with all the e's, which I'll do it really quick. Negative. No x primes, thank God. Just go right into this. This is equal to so C1 is equal to negative C2. Let's do the next one. Right? Plugged in for C1. You can pull out a C2. Remember, if mu is 0, C2 is going to be 0 because if mu is 0, lambda is not satisfied. That's the only way that this is true. So by default, we know that C2 is going to have to be 0 because mu has to be non-zero, right? So C2 is going to be 0. So x is going to be, and C2 is equal to C1 pretty much. So x is equal to 0, so that's only trivial. Right. Next case. This one's also going to be only trivial. So we have, whoops, our repeated roots. That would be C1 equals 0. Times x. So x of a is C2a, which is 0. So C2 is equal to 0. So you can see this is only trivial. If we have lambda less than 0, this is complex case. first condition here. Second condition, C2 sine a mu, set a mu equal to n pi, mu is n pi over a, right? So what makes sine of whatever 0, sine of n pi would be 0. So we set a mu equal to n pi. Mu is a value. So C2 is not going to be 0. So our lambda n would be negative n squared pi squared over a squared. The eigenfunction. Right? Yes, that's correct. This is supposed to be times x, not mu. Okay. Step 3. Solve for y sub n. Right, that's what we were given. So let's solve the second order equation here. I'm going to plug in for lambda here. It's negative, thank God. Okay. That's, oh, we have one of these again. Fantastic. So we're gonna need y prime for the boundary condition. Right. So then this y prime of 0 is n pi over a times c1 minus n pi over a times c2 is equal to 0. So c1 is equal to c2. I think that's great. So then y is equal to c2. You can plug in for either one. Pull out the c2. Which one is this? Looks like cosine to me, I think. It is, yes. So we have the plus there. I'm going to turn this into n's. This is 2 times cosh n pi over a times y. Two combines with the cn. Technically, it becomes a new constant. So now from here, we can write the general solution. I'm going to skip right to the general solution. Right, you understand the fundamental set of solutions, right? We're going to write the summation notation. We have c to the n times c to the n, so that's a new constant. Call it c to the n. Times, we have cosh. And then we have, I think, a cosine? Sine, sorry. And pi over a times x. Now, don't know why I have a t there. So why? Let's use the boundary condition with the value. Right? That's equal to plug in b for all the y's. And then solve for c sub n. That's going to be uh, 2 over a. I think this isn't... I could be wrong on this. Yeah, it's from 0 to a. Okay. 2 over a, integral 0 to a, g of x, sine n pi over a times x. So then the solution, u of xy is going to be the summation n equals 1 to infinity. I'm going to pull out this 2 over a. I think I can do that. Don't see why not. Yeah. So then this is all of this over this Wait, that's interesting. That is very interesting. Oh, sorry. We're good. I just thinking something. We have cosh n pi over a times y times sine n pi over a times x. This might be the record for the fastest PDE I've solved yet on this channel. Don't know if that's a good or bad thing. We didn't have to integrate, right? Not integrating makes this a lot easier. There's a part B to this problem. Let me show you quick. See it there? I'm not doing that. I could, it's not that bad, but I don't feel like integrating. You guys, this is not a video on how to integrate. It's on how to do Laplace's equation. Alright, well, this is the end for Laplace's equation on a rectangle. Hope you learned a lot. We're going to move on to circles and semicircles now. The solution is going to change completely. Almost. Same steps, but like we're going to have to look at it differently, and it's going to have to be solved differently. I'll give you a little hints. Euler's equation from second order ODEs is going to make a comeback. So anyways, I hope you enjoyed this video, and I will see you for the next one.